Cool. It's great to see everyone, although you're very small on my screen. And welcome remote participants. I'll be at Friday Harbor on arriving Sunday, so I'll have the week to spend with many of you as you work on your projects. So I'll be there to help out. But today, I wanted to give a lecture on some data science tools that might be helpful for you as you start to explore your different research topics on marine heat waves next week, and kind of go over some examples and applications of those too that I've come across during my years studying marine heat waves. So because I don't think I know any of you, I have a little introduction. So I did my PhD in oceanography at the University of Washington at the School of Oceanography. So I've spent I've taken many trips to Friday Harbor through graduate student retreats and different programs. So I'm excited to go back, and I'm sure it hasn't changed too much. It's kind of a timeless location, which is great. During my PhD, and actually in my master's too, I really focused on the drivers of marine heat waves from more of a physical oceanography point of view. So my master's was also in oceanography, and that was with Andrew Pershing, who I think you've heard from earlier in this week. So we were both at the Gulf of Maine Research Institute at the time. And right before my master's is when the marine heat wave in the Gulf of Maine occurred in 2012. And that was a really cool natural experiment in my mind of what happens when the ocean abruptly warms to a quite an extreme extent. And so that kind of trapped me into the research of marine heat waves, which was very ill-defined at the time. And so it was a great opportunity to get in and explore what these events are and have they happened before and will they happen again. So I'm from Maine, so I'm a Northeast coaster, and I was excited to, after my PhD, to go back to the East Coast for a short while, doing a postdoc at Columbia with Ryan Abernathy. So that was more focused on the data science, and so contributing to Python packages and kind of the open source Python community. And then that led me to my current position as a data scientist at a company called Jupiter Intelligence. So currently I'm in Boulder. We have an office here, a very small one. We're technically a startup, although there's a gray line between when you're a startup and you're just a private company. So we've been in existence for 8 years. I've been there for almost 3. And I really love my job. I get to work on a variety of climate science problems. So our main offering is to provide customers in the financial, financial, banking, energy, real estate industries, data on their exposure to different climate risks now and in the future. So recently I developed a wildfire model. I'm actually working on ocean temperature right now, which is exciting. But I've done a lot with analyzing large climate models and looking at different risks, including storm surge inundation and flooding. So while I'm not really doing marine heat wave research anymore, I still apply a lot of the skills that I learned in my PhD and my academic career in my day-to-day. So yep, I said I'm in Boulder. It's a picture of me and my dog. We like to go hiking in the Rocky Mountains a lot. No ocean here, but we find alpine lakes to go paddleboarding in, which is great. And I'm happy to talk about my career path too, if anyone's interested in what opportunities exist in industry next week, or for those who aren't there, we can chat offline or in the Slack. So happy to do that. But today I have a lot of material to get through. We'll see if we can get through it all. I might breeze through the intro because I think you've been primed on marine heat waves all week, so it might be redundant, but really try to get at the core, which is trying to present these data science techniques that you can apply to both oceanographic and climate data to study marine heat waves. All right, so again, kind of starting big picture, just because I think it's helpful. And I'm going to go through this quickly, but the Earth energy budget kind of compares the flows of incoming and outgoing energy. And these are relevant to the climate system. So in a stable state, the incoming solar energy would be balanced by what's going out. There wouldn't be many changes into the climate system, but that's not what it looks like today. There's much less outgoing energy compared to what's coming in, and that causes an imbalance. Most of that imbalance, about 91% of it, goes into the ocean. And so that's kind of one of the motivating factors of studying ocean temperature is how does that imbalance impact extremes in the ocean? I don't think we have time really to get into this schematic actually, but it's just to show you those different components of the Earth energy balance. And so in a stable state, you'd have the incoming equating to what's going out. As you can see, there is a very small number in the bottom corner, 0.7 watts per meter squared of an imbalance that goes mostly into the ocean and all that. Although that's a small number, it actually has a pretty big impact. So this has been, this imbalance in the climate system has been around for a while, and we can actually see that already in the observations of what impact that has. And so here I'm showing you two different time series and a corresponding spatial plot of different trends in both the sea surface temperature and the ocean heat content. And so we talked about this excess energy going into the ocean. Well, that materializes in a warming trend that you can see from in the top, the global mean sea surface temperature. So each of these wiggle time series actually represent different reanalysis products that combines both in situ satellite observations and does some kind of interpolation on it. But you can see that they all pretty much agree between the different products, which is really nice. See a lot of year-to-year variability, a lot of, you can even see decadal variability, but most notable is that starting in the 1970s, you see this more uniform warming trend, which is of pretty big concern. So you expect that as that imbalance heats up the ocean, that the temperatures are going to increase and rise. So that's the global mean picture in the top left. If we look at what that trend looks like from about 1970 to the end of through 2010, I think that's the period. At every point in the ocean, you can see on the bottom left where these temperatures are warming faster relative to other locations. So this warming isn't uniform over the ocean. Some places are warming faster than others, and there's many, many reasons for that, and a great PhD dissertation in itself. There's some places that are cooling even, but most of the warming trends, you see a significant increase in the most recent 30 years. So same with ocean heat content. So you expect that those temperatures at the surface will make their way to deeper layers, that there's fewer data sets that provide heat content data. So these are showing 3 from different products named after different people. They all show pretty good agreement, but that there is this slow warming trend over the course. This one's only going back to 1950 based on the data that was available, but definitely concerning the heat content in the ocean. So the upper 2,000 meters is warming. And if you look at that trend on the global map, you see that the North Atlantic and South Atlantic is warming faster than the Pacific, and the Southern Ocean is warming also. And the main reason for that is that in the Atlantic is where you have the most recent generation of deep water. And so that deep water at some point was at the surface. So the deep water, and deep water is this layer between 1,000 and 2,000 meters, that deep water in the Atlantic is the one place in the ocean that has seen the atmosphere most recently. And so you can imagine a lot of that anthropogenic signal has already propagated its way into the Atlantic and resulting Southern Ocean, whereas in the Pacific, it takes much longer for those waters to circulate. So that's kind of what has transpired from the observations. We can look at these trends. We can look on the map to see if certain areas are lighting up more than others. We can also look forward using climate models. So here's, again, sea surface temperature and ocean heat content going out to 2100. So this is the projected rate of change of sea surface temperature from CMIP6. So the IPCC, the most recent set of climate models. And this is for a climate scenario that kind of represents the worst case. So there are no areas that are cooling anymore. All the surface ocean has experienced some amount of warming. And again, it's not uniform. You can kind of see different currents and areas light up, and we can speculate as to why. And the same with the ocean heat content. Now looking at the upper 700 meters, the warming is much more consistent across the ocean basins, and with the North Atlantic and Southern Ocean having the strongest signal. So just an example of, thinking about how temperatures are changing and what this has looked like from observations, and then looking forward into climate models to see how we can expect those changes to materialize under different scenarios. So now I want to kind of shift our focus to not just thinking about changes in the mean and taking these large averages, but now thinking about what this means for the extremes. So we're pretty confident that the mean sea surface temperature is going to increase, but what does that mean for the tail of that distribution, so the extremes? So here's just the schematic of the imbalance. And so on the right now is kind of a representation of what the data statistics are. So the y-axis is the probability of occurrence. So this is a probability density function. So where you have the most area under the curve, that's the highest occurrence of that value likely to occur. So under the gray bell curve, this is a normal distribution. Under the gray bell curve, the average occurs most often. And then you have tails on that distribution of, cold and warm temperatures. Under a normal distribution, the likelihood of a cold and a warm temperature are about equal. If you shift the distribution to the right, so you change the mean and increase the mean so that it's warmer, you could either have just a shifted PDF where, again, your chances of the cold and warm there's the same likelihood, but now you've also increased, if you compare that with the original distribution, you've increased the area under the curve that used to be extreme. So now you're going to get, relative to the baseline, this gray bell curve, you're going to have more hot weather or warm temperature events. This can also not only affect the shift in the distribution, but the shape of it as well. So if your distribution were to spread out, so the tails get fatter, you'd have a higher likelihood of extremes in either cold or warm. So how can we apply this to, we'll go through an example of how we can apply this thinking to a time series to identify marine heat waves. So here's just a synthetic time series where time is on the x-axis and the y-axis is a temperature anomaly, sea surface temperature anomaly. So anywhere where it's positive, yellow, it's warm, anywhere it's blue, it's cool. And this is meant to represent a stationary climate. So one where there is no imbalance, your chances of getting a extreme warm event and an extreme cold event are equally as likely. So from this time series, we can create that PDF, that probability density function, and we can calculate what a standard deviation is. And we can use that as a threshold to pick off these extreme events. So pick off those events that might be in that tail of that distribution. And we can use different thresholds. So here I'm showing 1 standard deviation, but you could do 2 as well. And then you can start to see and count maybe how many days that temperature exceeded that threshold. Now, let's introduce climate change and see what would happen to this way of thinking about marine heat waves. So now at the very end of this distribution, the climate is warming, and you can kind of see a trend in this time series where these really warm temperature anomalies are much more frequent now than the cool temperature anomalies. So you still get cool anomalies, but the warm anomalies are much more likely. Right, so this is indicating that, like, with climate change, the frequency and even duration of those warm anomalies are becoming more frequent. And I just saw, okay. If there's a question, also just raise your hand, because sometimes I might not see the chat, but I will try to check it. Okay, and then, I haven't spent too much time on the ecological impact side of things, but as you increase the warmer temperatures, you're getting into this range where species like whales, coral reefs, fish, sea lions, different mammals, they haven't seen those temperatures before, and so they're unable to adapt and therefore become more vulnerable, and you see a lot of the impacts, they're more visceral. So this is an interesting component too, because I think a lot of our awareness of marine heat waves really stemmed from the impacts. So, we saw fish wash up on the shore, we saw sea lions struggling, and so it kind of wakes the human side up to what's going on in the ocean and makes it a little more urgent to understand. So we talked about these different thresholds. So this red dashed line maybe is our marine heat wave threshold. And we want to now categorize the events that exceeded this. So let me go to the next slide. Yeah, so this is just showing that these temperature anomalies that have surpassed this threshold are what we're going to define as potential marine heat wave candidates. We might impose some other criteria for classifying them as a marine heat wave or not, such as duration or time of onset, things like that, whatever is relevant to what you want to apply it to. And I know you've had some talks earlier in this week about how to define marine heat waves, so this is probably a familiar figure. I think it was, yeah, Alistair Hobday and Eric Oliver. So similar to those diagrams I showed previously, you have your black line is your time series of temperature. You define some kind of normal, some climatology of what you'd expect the temperature to be like in that given period. And then whenever the observed temperature is above that climatology, then it's a anomaly, a positive anomaly. Furthermore, you have a threshold on top of that climatology that will tell you when those temperature anomalies are extreme. And so then you can flag those and analyze, okay, how long did this temperature anomaly persist above this threshold to get some kind of duration? You can look at what was the peak intensity over that warming event, when did it start? And then you can calculate, the rate of onset from when it started to the peak. Some of these marine heat waves happen very quickly. Some of them evolve slowly over time. And if there are, spikes in temperature at a given location, maybe you don't care about these as much because they're so short-lived. So maybe you want to ignore those. So those are some of the characterizations you can pull from these time series. I'm just being mindful of the time because it's supposed to be quick. And then this is a map of, where these marine heat waves have occurred in the past. So mostly where there's people is kind of what I find, but where there's those impacts to the fisheries and, where people are. So another just timeline that I have to update. I think there's been quite a few since 2020, but just shows you the frequency of these reports of marine heat waves happening in all parts of the world. And it's really interesting to dive into each one and understand how they differ from each other and get a sense of, what's driving these events and what their impacts are. Speaking of drivers, this is kind of segueing into the next middle part of the talk. I think I've alluded that no two marine heat waves are alike, but you can probably categorize them into two types. So one is marine heat waves that are more ocean driven and ones that are more influenced by the atmosphere. And so I have two examples of each of these. We'll start with the ocean. So there was a marine heat wave in 2011 off the west coast of Australia. This area has a countercurrent called the Lewin current that flows from the equator to the pole along the coast. And that current brings warm water south. And during this year, there was a really strong La Nina. So there was much warmer water in the Western Pacific. There was a pressure gradient from the Indo-Pacific down off the coast of Australia. And so essentially what that caused was a surge of the Lewin current, which brought warmer water to this region and essentially caused the marine heat wave. So, that's one example of ocean heat wave. There's been others, but usually they're caused by, a surge of warm water. Maybe there's sluggish circulation of cold water nearby. So a lack of supply of cold water to the area, so it was able to warm up. Reduced vertical mixing, and I mean in the mixed layer, so cold water being entrained from below to cool the surface. And then another driver could be the reemergence of warm anomalies. So say you have a marine heat wave one year, those anomalies can actually mix below the mixed layer in summer when it's shallow, and then in the winter when it deepens again, those warm anomalies can be reintroduced to the surface and help amplify a marine heat wave the following year. So there's some memory that the ocean has that can contribute to marine heat waves. Another type of marine heat wave, as I mentioned, is one that's more affected by the atmosphere. So an example that I love is the 2013 to 2015, a very long duration marine heat wave in the Northeast Pacific, also called the blob. This huge marine heat wave was really caused by what was coined, I think, the ridiculously resilient ridge. So this high pressure system. And if you think on land, when there's high pressure over where you live, it's very pleasant weather usually. It's very warm. There's not a lot of clouds. There's not a lot of wind. So those all can happen over the ocean as well, all those types of weather events, and it leads to positive surface heat flux into the ocean, and so warming of the surface ocean layer. Usually that's also accompanied by lower relative humidity, so there's less evaporative cooling, warm air temperatures, and so that can really cause these really big marine heat waves over large swaths of ocean, because the atmosphere, again, their mesoscale variability is quite large, whereas for ocean-driven marine heat waves, usually those are more intense and localized because currents are the scales aren't as large as these big weather events. So that's just a little overview of two primary types of marine heat waves. I wanted to touch back on how we might diagnose a particular event. So how do we know it was the shortwave radiation that was contributing to the event, or how do we know it was the ocean currents? So one way in which we do that is we devise what's called a heat budget in the mixed layer. So the mixed layer is just the upper layer of the ocean, 20 maybe meters deep. It varies throughout the ocean, but it's the layer that's very well mixed. And so this layer is very important because it's what interacts with the atmosphere. It's also where animals like to live. So you think of impacts, it's pretty important for understanding the tolerance and vulnerability to different species living in that layer. And the mixed layer does undergo seasonal variation in most of the oceans. So in the summer, it's very stratified. You have warm temperatures confined to a very thin layer at the surface. You have a much kind of wider thermocline, but in the winter, when there's storms and more wind, that mixed layer can deepen. And so it's generally much deeper in certain areas in the winter. So within that mixed layer heat budget, we know the change in temperature in the heat budget, in the mixed layer. So we want to quantify the contributions that change that temperature over time. And those contributions come from the net surface heat flux. So the downward radiative flux hitting the surface of the ocean. It comes from a advection term, so both zonal west to east and meridional south to north flows of water that affect the temperature change within the mixed layer. It can also come from vertical entrainment, which I mentioned earlier, which is mixing of that cold water into the mixed layer to cool the temperatures. And it can also be influenced by, horizontal and vertical mixing from different eddies. So oftentimes, because of the data limitation, we can't always quantify vertical entrainment or vertical and horizontal mixing. So those are often put as a residual term in the heat budget. And most of the time for marine heat waves, the net surface heat flux and advection terms can be the dominant drivers and can really tell most of the story without having to get into these fine scale, complicated contributions that require much high resolution data that isn't really accessible for these large scale studies. So two examples of implementing this heat budget for marine heat waves were done by Dylan Amaya in his paper in 2020. So looking at the 2019 heat wave in the Northeast Pacific. And I'll just start with that one first, ignoring the one on the right. So to construct his heat budget, he pretty much plotted a map of sea surface temperature anomalies. And he drew a box around the area that had the most warming. So this is the heat budget box. So it's space, and then there's a depth that he's averaging his heat budget across. So you kind of want to define an area that is most interest to you. And then on the bottom is a time series. So he's gotten data, probably from reanalysis, I believe, of the different components that he can then, of the heat budget that he can then quantify. And that time series extends back to 1980 and goes through 2019. So the heat budget should sum to the change in mixed layer temperature. That change in mixed layer temperature is shown by the blue line. So if you look, you can see that 2019 was the warmest year on record that between 2019 and 1980. So it's just showing how extreme the anomalies were in that box that he identified in 2019. So he's going to show these other terms that then sum to equal that change in temperature. And as I mentioned before, often, vertical entrainment, horizontal and vertical mixing, they're grouped into a term called the residual. So that's the gray line at the very bottom. And then he's also quantified the contributions from advection, so that's the brown line, and then the contributions from surface heat flux, which is the red line. And right away, it's very clear that the atmosphere was the big component to this story in 2019, the major driver, with some cooling contributing from the residual term. So that could be from the vertical and horizontal mixing or the entrainment. but that the advection term was pretty negligible. So it's pretty much zero for actually most years in this location, which is interesting. So these are the anomalies to the temperature change. So overall, what this is telling you is that the atmosphere in this location is very important for controlling temperature fluctuations in this region, and that in 2019, that was particularly the case, that this was an atmospheric driven event. Now, Eric Oliver also did this in 2017 for a heat wave near the Tasman Sea off the southeast coast of Australia. And again, looking at, he's only showing the 2015 to 2016 anomalies. So this is kind of integrated from the start of this marine heat wave. That's why it starts at 0. It's being integrated across. And in this case, the total temperature change in the box that he identified was pretty much matched by advection, and that the surface heat flux actually had some role in cooling the vent towards the end of the marine heat wave. So the ocean helped to terminate the vent. The atmosphere helped to terminate the event at the end of the marine heat wave, but it was mostly driven by ocean advection. So 2 completely different marine heat waves using the same method, showing very different results. I think this is a really nice example of trying to get at what were the main contributions to this event and the main drivers for why it was created. And of course, that's just a very small, if you're looking at marine heat waves with a microscope, right? The mixed layer is a pretty small time and space scale, but I want you to realize that these drivers of marine heat waves happen across a range of time and space scales. And so this is a plot by Neil Holbrook that he developed, which is showing different spatial scales in the ocean from 1 kilometer to 10,000 kilometers, and then different time scales from a day to even 100 years. And so on the very small space and time scales, you have those processes that are happening in the mixed layer. So down the bottom left, you have the air-sea heat fluxes, vertical entrainment, eddy process, ocean advection, wind stress. As you get to longer time scales and longer spatial scales, you start to get more of atmospheric changes to atmospheric circulation. You have interseasonal modes of variability. You have different processes going on in the ocean, such as Kelvin waves, that can influence marine heat waves. So these are kind of indirect drivers to the heat budget now. And as you get out to much larger time and space scales, then you're talking about interannual modes of variability like El Nino, Indian Ocean dipole, large ocean atmospheric Rossby waves that can go across entire ocean basins. And then at the very highest scales, you have that long-term climate change, that imbalance impacting. So it's kind of a cascade of drivers, influencing what's going on in the mixed layer. Okay, so we're halfway through, and I wanted to talk a little bit about, now that we have gone through maybe one way of quantifying the drivers of marine heat waves, we can talk a little bit about what data sources might be useful and their applications. So this is more for a reference. I'm not sure if students have their own data sets for the projects later on, but I wanted to present some options, and the use of this will depend on what your question is. But there's kind of different categories that I see. So the first is in situ observations. So these are providing direct measurements of ocean temperature. They have very high temporal and spatial resolution. There's a few different examples. So moored buoys, these are fixed buoys in the ocean that have very high temporal frequency. And in the Pacific, they're spaced from 1 degree to 10 degrees apart. So the NOAA Tropical Atmosphere Ocean Array, TAO, is what's often used to monitor El Nino. So there's a lot of great data, long-term data there. and it's continuous or very real, very near real time. So these are good for studying temporal variations in marine heat waves, looking at the onset at particular sites. So another one is ship-based surveys. So these can be more regional. Again, they also output very high resolution data in targeted areas where the ships are. And they have actually a pretty good record dating back quite a ways. So they also have helped inform a lot of our estimates of ocean heat content. So they're very important, but expensive to, to go out and collect data on ships these days. Argo floats are really cool. I've used Argo floats in my own research. These are kind of free drifting floats in the ocean that can profile the upper layer. And there's some floats that go to the deep ocean. They do offer more broad spatial coverage and regular temporal updates. They're pretty good for tracking large-scale marine heat waves. And there's some data sets out there that have gridded Argo float data, so it's very easy to access. So the Remick and Gilson climatology is one data set. So it's you don't have to go and download 10,000 float data profiles. There are some products that have gridded these for you. Not mentioned on here, but for in situ, there's other coastal and nearshore monitoring stations. So that could be like tide gauge stations. These are pretty important for looking at the impacts of coastal ecosystems and fisheries due to marine heat waves. There's also drifters that pretty much drift with the ocean currents that can measure sea surface temperature, and then gliders. I haven't had a lot of experience using gliders, but that's another option for collecting in situ data. Okay, so for remote sensing, this is more related to satellites. So they offer a much broader spatial coverage and can allow you to characterize the large-scale patterns of marine heat waves. There's a few different products mentioned here. I can quickly go through. So the advanced, very high resolution radiometer satellite. This is a NOAA-based satellite. It's been collecting sea surface temperature from the 1980s. And so it offers, some long-term use of studying marine heat waves, and that data is daily. Then there's MODIS, which can provide high resolution sea surface temperature data in near real time. And that's good for looking at the large scale and the fine scale temperature anomalies in coastal and open ocean environments. So, and then there's, I think it's GRIST. I'm not sure how to say that acronym, but the Group for High Resolution Sea Surface Temperature is another satellite-based product that you can use as well. They each have different kind of resolutions. And then there are the good old reanalysis products. So these are more consistent data products that offer global coverage, various temporal resolutions. NOAA OISSC have an asterisk because it's not really a reanalysis, but it's more of a blend of in situ and ship-based observations. But these are very helpful. They often have some of those heat budget terms in them. So if you're looking for doing a heat budget with data that is produced in a consistent way, reanalyses are very helpful. And then for climate models, of course, these are good for understanding the changes to marine heat waves over the long term and under different climate scenarios. So the GCMs and Earth system models are good for, how marine heat waves might evolve under different climate scenarios. The regional climate models and different downscaled models are good for understanding more localized marine heat waves, maybe in regions with complex dynamics. Earth system models, I will mention, also have often biogeochemical variables, or variables that can help you understand the biogeochemical changes during marine heat waves as well. So that's an additional bonus. So for each of these data sets, I just wanted to provide some examples of maybe what they look like. So in situ, they can be a little more sparse, but still have very good data coverage, higher temporal, hold on. Higher temporal resolution, but they are, there's much more effort to go and collect these, right? Especially if you're talking about ship-based observations. Remote sensing, it's much more continuous and smooth. Some of these satellites have a hard time seeing through clouds, so there have been some interpolation methods applied post-processing. And then again, with the climate models, you're able to parse out the changes to marine heat waves under different future climate scenarios. So how do you get this data? So there's a few different places where this data is available, and I've grouped them based on these categories. So I'm not going to go through all these because of time, but I'll share these slides with you so you have this reference. And then if anyone needs help obtaining data, I'm more than happy to assist. But they are, all these data are pretty widely accessible and free. So, all right, we are cruising through here. So just some common data formats. So depending on what data you end up using, they will come in different formats. So the most common that I've worked with is gridded data. So, if you're dealing with remote sensing data sets, reanalysis, or climate model data, there's multi-variables within those data sets, and they cover both time and space. So you could have 2D, 3D arrays, and some of the kind of data format types. Most common are NetCDF, ZAR if you're working on cloud resources. So these are optimized for like AWS or Google Cloud Platform. And then there's GeoTIFF, SCRIB, and HDF files, which are a little less common, but you might run into those as well. And then there's point-based data. So these might be more for in situ observations, a buoy, a tidal gauge that's collecting temperature observations, or a ship platform. So these are fixed location usually, and may include a time series. So these may be CSV, text files, ASCII, all these different data sets. You can open them up in Python. There's a few different libraries that I use often is Xarray, which is good for those gridded data sets of NetCDF, ZAR. Pandas is good for CSVs. And then GeoPandas and Rasterio are often good for dealing with GeoTIFFs, things that have more geospatial information associated with them. Okay. Feel like I'm talking fast. I'm going to slow down a little bit. Okay, so the next 15 minutes or maybe 10 minutes or so, I wanted to run through actually kind of already talked about this. I'm going to skip forward a little bit because we have about 15 minutes remaining, and go through one example of studying the subsurface. So we talked about kind of dissecting a time series of temperature to characterize marine heat waves. We talked about a heat budget to understand what the drivers are locally. Now let's maybe characterize what's going on in the subsurface. So in this example, we're going to leverage Argo floats in the Northeast Pacific. So the kind of premise behind doing this was to compare two different marine heat waves that kind of happened in the same location, but different years. So on the left is that 2014 marine heat wave called, the blob. And then in 2019, it came back as blob 2.0. So you can see the spatial patterns in those maps look fairly similar. And then the diagonal dashes are representing the locations that are actually considered a marine heat wave based on I think it was the 90th percentile of temperature at that location. So if we take a box again, like the heat budget, so I drew a box in the Northeast Pacific, and then I took the average temperature anomaly within that box and plotted it in the middle. So you can see that 2014, those red dots are signifying that there's a marine heat wave. It's pretty extreme and pretty persistent. Then it cooled for a while, a few years, and then in 2019, that warming came back. You can also then, in that same box, take the average of the subsurface temperature anomalies, and you see that in 2014, indeed, like there's a really big warming signal in the subsurface. That warming signal persisted. It looks like it propagated downward. Then it cooled at the surface. 2019, warming came back in the subsurface. So we kind of want to understand what was going on to contribute to those subsurface anomalies. Okay, so I'm going to skip a slide here. So now I'm using a single point, using Argo data in a single point. And just trying to move that around. Okay, so the map in the top right is the Northeast Pacific, and that star is representing where these Argo floats are coming from. So these are a time series plot, but showing depth. So the x-axis is the year, and the y-axis is depth, so pressure. And on the y-axis, you can see little notches, black notches. These are actually where the observations are available from the Argo flows. So we are interpolating a little bit in between those observation depth points. I think it was every 2 meters or so. So what can you see? These are the actual values of temperature, salinity, and density. And there's definitely a very strong seasonal cycle in this area of temperature and salinity, and therefore density. So in the summer, it tends to be warm and fresh, less dense. In winter, cool, salty, and denser. But you can kind of see something weird going on too in the raw data, even without taking the anomalies. The salinity seemed to be extremely fresh in 2019 compared to 2014. So that kind of piqued my interest into maybe that was a differentiator between these two events happening in the same location, just years apart. So then we can remove the average from the data to get the anomalies. And this really does highlight that salinity anomaly where there was more, there was a freshening of the subsurface really caused by precipitation. And that connection to precipitation was an additional analysis to look at what the precipitation fields were doing during that time. So let's see. So the density surfaces can kind of give us a sense of what the mixed layer is doing as well. And there's 3 different density surfaces represented. The first one is kind of within the mixed layer. So you can see that it outcrops at certain times of the year, but there's definite warming in the mixed layer in 2014 and 2019. There was that net freshwater influx in 2019, and that caused the surface density to be lower, so maybe more buoyant because of that warm and fresh water occurring. So then that kind of led to explore what this buoyancy factor had to do with the temperature anomalies, and did it have any influence on the marine heat wave in 2019. So one way you can quantify the buoyancy is using a bulk stratification anomaly. So this is shown in the time series here. So it gives a sense of how buoyant that upper 200 meters-ish was. And when you compare 2014 and 2019, the buoyancy was much greater in 2019, likely due to that freshwater input. And that really helps to stratify the upper ocean, prevent those warm anomalies from mixing downward. If it's so buoyant, it can't mix. So that can increase or enhance the warming in the upper ocean because of that freshwater flux. creating more buoyant water in 2019. So we're getting to a story here. 2014 and 2019 at the surface looked very similar, but what was going on beneath the surface really set them apart. And it was really that freshwater flux from precipitation that caused higher buoyancy and therefore helped to amplify the warming in 2019. Okay. This is kind of leading to another main conclusion that tracking these anomalies as they propagate downward into the ocean, that they tend to persist even beneath the mixed layer. So once they get below the mixed layer, it's very hard for those anomalies to dissipate without, strong advection or recirculation. So there's some type of memory of surface anomalies as they get out of the mixed layer and get into the deep ocean. And that is shown in the bottom plot too. So these colors represent different layers of the ocean. So the red is the upper, red is about the middle, and the orange is the deep. And deep is, 280 meters. So these vertical bars on the top kind of showing those layers. So you have the biggest heat content anomalies in the upper ocean, where those the atmosphere is changing the temperature more rapidly, but as you get deeper, those anomalies become more diluted, but they persist way longer than when the surface anomalies cool or go back to normal. So this was really fascinating. One way of using Argo data to kind of characterize these marine heat waves and their longevity. Okay. So, and again, you can tie this back to climate change. In a future warming world, we're going to have more stratified oceans and less mixing between layers. And so that increase in stability can enhance warming in the upper ocean and amplify marine heat waves in the future. Okay, so that's one example looking at a particular location. I wanted to emphasize that these marine heat waves, we saw that they can persist for a long time, but they're also, the ocean is fluid. These anomalies can move around. And if you're just fixated on one point, say this X on this map, you can see during the Blob 2014 event, yes, that area had some pretty intense anomalies, but it did pass through that one point. And so if you just are fixated on one point, you might miss the whole story. And that kind of leads to other scientific questions related to trying to track these events and characterize their duration, persistence, and evolution. I have a section talking about this. So I actually implemented some techniques from image processing to pretty much extract marine heat wave data from sea surface temperature. Sorry, I'm going backwards here. So you have a map of anomalies. You want to grab those that are marine heat waves. You get this binary image of, yes, it's a marine heat wave. No, it's not a marine heat wave. And then you can start to do some processing on this image to try to close this pixelated image into more of a contour. So that way, instead of just pixels in an image, you have these blobs or contours of anomalies moving around. And it's not showing the rest of this. So what this results in is the ability to identify a marine heat wave and then track it in time. And so this is the 2012 marine heat wave in the Gulf of Maine. And you can see that's pretty localized. It didn't go too far, but it's changing shape and kind of moving around. And then you can start to quantify how long this event persisted in totality. So about 8 months. The plot on the lower right is like a heat map of where the marine heat wave hung around the longest. You're going to have more of those high intensity anomalies. So this is in degree C months. So the Gulf of Maine definitely was in one of those persistent areas for this marine heat wave. I'm gonna kind of wind down here now and talk about some tools you can use to facilitate your research. And so I code mostly in Python. So a lot of times I really like to use Jupyter notebooks, and I'm sure most of you use these as well, but it's just a nice way to visualize your data in one place as where you're actually computing your data. And so you can also include Markdown to add descriptive text. And it's just a really nice way to organize your code and make it reproducible. The other thing I enjoy using is GitHub. At my own work, we use GitLab, which is more of an enterprise level of it, where you can keep track of different versions of your code. And you can add your Jupyter notebooks to GitHub as well. It's a good way to collaborate. So if you and someone else are both working on the same project, you can make changes and share them with each other, add documentation. And eventually, if you come up with a tool you think is helpful, you can actually make it into its own Python package that others can contribute to and deploy for their own research as well. So it's a very open source and collaborative way of sharing your research. Often many publications too require this at some point. And then this is a more of a reminder, because I'm sure we all have seen schematics of what makes a good data story. And this has also implications for scientific analyses as well, all types of scientific analyses. So, you know, as I set the context with the subsurface marine heat waves, introducing these two events and how they were in tension with each other and how we wanted to figure out what was going on and what differentiated them. You want to set the context of why this is relevant. You define the problem or the main question or challenge. So one example could be like, how is climate change influencing the frequency of marine heat waves over time? And then I think the most important is showcasing those insights from the data that you're analyzing. So what's most important and what's most impactful and visually compelling to relay that information to your readers or your captive audience. And then providing an interpretation. So, you know, this marine heat wave was affected by buoyancy. We can see that in the future, the buoyancy is going to increase. And therefore, you know, these marine heat waves could amplify in the future due to the stratification changes. And then tied into explaining the significance and the impact and maybe what else is missing from our understanding collectively and what else could be done. And part of that, you know, going back to the showcasing our key insights, there's just endless amounts of cool visualizations you can do. I just wanted to highlight a few of them in the last 2 minutes here. You know, you can do small multiples of different plots on the left, like Eric Oliver, you know, a map to, oops, let me go back here, a map to orient the reader to where the location you're talking about, maybe looking at some historical context, pulling out the relevant marine heat wave data. And then at the very bottom, what you've calculated. So the duration of events over time, the intensity to kind of help tell your story. Other plots that I enjoy looking at are Hobmiller diagrams. So it's just showing you almost the propagation or movement of temperature anomalies in time and space. So you can see this is an example in the equatorial Pacific with El Nino of temperature anomalies moving across the equator. And those dashed lines, then the author pulled out showing where the Kelvin waves were propagating and moving back and forth to transport cool and warm water. I showed an example of looking at depth profiles, and animations can be very impactful too if used right. Okay, so I don't want to go over. I had some research questions that if I could do another PhD, I might entertain. So I wanted to throw these out to you, and if anyone is interested, feel free to take these and see what data sources are relevant and what methods would be needed to tell a story. So what are the early warning indicators and precursors to marine heat wave events that can be detected using oceanographic data? So this might lend itself well to some machine learning applications of predicting marine heat waves in a physically interpretable way. So that's really exciting. Do marine heat waves interact with other extreme events? So maybe hurricanes, ocean acidification, and what are the impacts and how are they amplified? A lot of depth to that question, very fascinating. And I do have some examples of some work that has been done to look at that, but it's very preliminary. I still feel like this is the early in this kind of area of research. So a lot could be done there. Do different oceanographic regions respond differently to marine heat waves based on their physical characteristics? So that's more of a regional focused. And then one that would be more collaborative, I think, is how effective are current mitigation strategies in reducing the impacts of marine heat waves? And then how can they be optimized using data-driven approaches? So that, would need to understand what those mitigation strategies are, probably in terms of fisheries, and then how have they been implemented and what effect have they had on the impacts. So that is all I have, and we are at the top of the hour. Happy to stick around for questions. I'll be in Friday Harbor next week, so I'd love to chat with all of you, and I'll be on Slack as well. So,
great.
Awesome.
Thank you very much, Hillary.
Of course.
So if people want to ask Hillary questions, why don't you do that? And you'll need to unmute yours, and I will mute mine while you're asking. Okay, go ahead.
Thank you, Hillary, for your presentation. I have a question. In the analysis of the marine heat waves with Argo floats in the North Pacific between 2014 and 2016, you only removed the total mean, but didn't remove the annual cycle, or?
Yeah, so from this plot, I think you're talking about, this one is the total field. So this has a seasonal cycle. For the anomalies, we did take that out. So it's the mean minus the seasonal variability. So it's just looking at the trend and the anomalies in there. So these are monthly. Sorry.
Can you start again? Because I think I didn't quite turn the volume on quickly, and got you at the very beginning.
Got it. Okay, so the question was about the Argo profiles and the seasonal cycle being in the anomalies. So this is the picture of the fields from the Argo data. So it has everything: seasonal cycle, mean, trend, variability, and then we subtracted the mean in the seasonal cycle. So these anomalies represent the variability, but also the trend as well over that 15-ish year period. So so there's no seasonal cycle present in the anomalies.
Thank you.
Thank you. Okay. Got it. And I will throw these slides up on I think it's called Box is where we're putting the presentation. So I'll do that after, so people have access to these.
Okay.
Hello, Hillary. I have a question. Is you talking about when do the mixing layer depth or about the marine heat wave heat budget? you mentioned the entrainment is really important factor for marine heat waves. However, in previous research, either by Oliver or Amaya, and their research seems don't mention about the entrainment or give it a qualified result. So is there some difficulty to do the calculation of the entrainment? Thanks.
Yes, exactly. Yeah, so there's a lot of processes that get lumped into this residual term, including vertical entrainment. And you can get that term, but it requires really like high spatial resolution data with depth as well. And with these two studies, they're using general reanalysis data that's more that they don't have those terms quantified. So I think it was more of what was accessible to them to compute. But yeah, the residual term can be computed. It just requires really high resolution data. And I did it from a buoy once. I'm forgetting how, but it was from it was from the tau array. So we had really high resolution vertical profiles of temperature, salinity, density, depth. But I think with the reanalyses, you just can't get that. So they just, whatever is left whatever they can't close from the budget, they just throw into residual, and they try to explain it based on, the other components of that equation that they can't quantify. I think in both cases, though, I mean, for the Pacific, it does have quite an impact in cooling the event. So usually that's indicative of the vertical entrainment, mixing cool water from below. And then in the Oliver case, it's kind of bouncing around zero. It doesn't really have much of an impact either way. I see a hand. Anthony.
Thank you. And the second question is for this on the left, Amaya's result and Oliver's result, they conflict with each other. So the difference because they use different resolution data set, or they considered about the surface and the maxillary depth budget. So what caused the different conclusion in these two research?
Well, so it's based on the event. So the conclusion for the Northeast Pacific was that the surface heat fluxes were so large and positive during this event that had the largest influence on the temperature change in the mixed layer heat budget. These plots are showing the data a little differently. They're showing the same conceptual idea. The left is more of a time series, so they computed this heat budget over all the months between 1980 and present. So you kind of want to focus on the very last 2019 point for the marine heat wave event. The left is more of an accumulation of temperature anomalies over time. So it kind of shows what the temperature change was like over time, over the duration of that event. So at first during this event, the surface heat flux didn't have much of a role at all. And then towards the end, it actually worked to cool the event. So it's negative. So these are just, again, the difference between an atmospheric driven marine heat wave and an ocean one. The heat budget is showing those contributions. One is more atmospheric driven, one is more ocean driven. So that's the difference.
Last question. Here,
Mm-hmm.
this work is about the mixing layer depth budget. But for the ocean ecosystem, do you think it can be a better choice for the heat budget over a euphotic zone or a mixing layer depth? So which one can be a better choice?
Yeah, so that's a good question. I think so the mixed layer depth and the variability in it comes into play for the heat budget. So it's very important. So as long as you define the photic zone doesn't really change in time, right? It's just constant. I've never seen that applied, but I'm wondering if it's possible. So you're saying instead of using the mixed layer depth, use some other depth that might be relevant to ecosystems and doing the same analysis.
But difficult for the
It'd be a little
modeling
harder to interpret.
work.
Maybe if you had you had the ocean and an atmospheric component to the heat budget, explaining the processes of entrainment would be a little non-physical to me because it's just some imaginary depth rather than, the mixed layer depth. But it would be interesting to pursue. Was there another comment?
I would put in a comment that you actually want to follow both, because looking at the depth of the euphotic zone relative to the depth of the mixed layer tells you whether you're going to be able to support primary production or not. So I think, in terms of doing the heat budget, you really do need to follow what's going on in the mixed layer, but then you also want to be able to monitor, the different, how the euphotic zone is changing, right? Because, in the springtime, if it's not until the euphotic zone becomes, you have to look, for the conditions for a phytoplankton bloom, it's the difference between the mixed layer depth and the depth of the euphotic zone. So I think you really want to follow both. From a physical perspective, I think the mixed layer depth is more important in terms of, assessing, doing the heat budget. But then taking the next step to look at what the biological response is, you really want to then look at the euphotic zone relative to that.
Right. Okay. Yeah. Excellent.
Laurie, thank you.
Okay. Other questions from?
Hi, Hillary.
Anthony.
I'm a PhD student at Scripps Institute of Oceanography. And I guess my question was a little bit more higher level. So you kind of showed this schematic, which I thought was really interesting when you were talking about the timescales of oceanic versus atmospheric heat waves. And I guess I was wondering, comparing oceanic driven marine heat waves versus atmospheric driven marine heat waves, are there any differences within duration? Like you kind of mentioned, like ocean advection, and then I was thinking, okay, maybe ocean-driven heat waves timescales are a little bit shorter, but then I kind of saw this schematic and I was like, okay, maybe they're a little bit longer. So I guess in your kind of analysis, do you see one typically being longer on different timescales than others, or you say they're about the same?
Yeah, that's a great question. Schematic is a little busy. Generally, so from a physical driver point of view, the atmosphere, the variability in the atmosphere is much larger than it tends to be in the ocean. And so any anomalies in atmospheric flow, so on here, there's atmospheric blocking, which those ridges of high pressure can stall for several weeks, cover like huge scales over the ocean. And so that imprint on the ocean tends to be much larger than a shift in ocean currents. But I guess El Nino would counteract that. So we can ignore El Nino. El Nino is a coupled ocean atmospheric process, but if we look at, you know, the marine heat waves around Australia that tend to be more influenced by diversions or intensifications of ocean currents, those are much more localized to those boundary current systems, in which are having most of the variability. So even eddies spinning off the Gulf Stream, you think of the space scales of those, they're much smaller than, you know, the effect of these large scale atmospheric changes happening. So it's not like a black or white, but I think that the atmosphere driven events tend to be much larger than the ocean ones overall. That's just the spatial scales. Temporal scales,